Hello, I am Mr. Fixit from Yes Repair. In this video, I'm going to show you how to use or show a demonstration on how to use the ADS1115. In the first video, I showed you the introduction to it as to what it can do. The second video, I showed you the configuration registers and how each bit is set and what each bit is sets the configuration for. So in this one, I'm going to show you how to actually communicate with it using the Arduino Uno R3 board. As you can see here, it's currently doing some tasks, and I got everything connected. So let me go ahead and show you what to connect and create the program so we can communicate with it.
To do this, we're going to use the address pin, which is this one here, pin 10. We're going to connect it to pin 7 on the Uno R3 board. Keep in mind we're going to need that later. Here we are going to use the address pin default value, which is going to be address 0x48. Now, it's always recommended to ground the pin if you are going to use the default value. Even though that the ADS will use it by default, it's best not to leave the pin floating because anything can cause the address to change while it's floating, and you do not want the address changing on your programming. So if you are going to use a default value, be sure that you ground the pin. Next, we have the 5 volt. I got it connected to the 5 volt pin here. Ground, as you can see here, it's connected to the ground. That's for the power supply. Next, we have the I2C clock. This is the serial clock, which is connected to pin 18. Now, on the Arduino board, you can use either pin 18 or you can use pin A5. That whichever one is more convenient for your wiring, you can use those two pins. For the serial data pin, you can use either pin 17 or you can use pin A4. Again, it just depends on your wiring as to which one is more convenient. And as you can see, this is all there is to set it up. Now, we're going to use this pin right here, which is pin 1. This is A0, input A0, if you're using a different version of the ADS. So you want to use A0. And that's it. That's all we got here. Now this pin here I have set connected to the 3.3 volt, which is this one here. I don't have it in the diagram, but that is the pin. This is what's connected to the pin here. So we'll come back to that in a moment. Now we're ready to go ahead and create a program to use the ADS. Here is a demonstration of the communications and using the ADS 1115. This is a short program. This just used to show you how this is going to work and how it's flexible. Now, the first thing we have to do is the first line. Now, as you can see, all the lines are numbered. So if you do have a question or you see a problem, you can always reference the line and refer to what the problem or what question you might have. So as you can see, the first thing we're going to do is we need to include the wire library. This is for the I2C. And the reason for this is because instead of you trying to figure out the timing cycles to send and receive data on the I2C bus, the library already takes care of that. So as you can see, it makes it very simplified. And instead of having to remember all that, all you have to do is send the instruction, the Arduino will do the rest. Next, we have the addresses. Now, you have 4 possible addresses. You can use address 48, 49, 4A, or 4B. That just depends. Uh, 48 is the default. So if you're going to use a default, then you can use this. Now, this is only my reference. And I do this is because instead of me trying to remember which address is which, I could just use A, B, C, or D. makes programming a lot simpler when you're dealing with multiple devices. You don't have to remember which address is which. Next, we are going to do variables. Now, we're going to set up the variables to uh, contain data from the ADS and our converted data. First thing we need is we need a unsigned integer of 16 bits long to contain the raw value. This is the value that we're going to receive from the ADS. Well, next we're going to use another unsigned integer, 16 bits long, to contain the converted value. Now, this is going to be the final result. This is going to be the voltage that we're going to detect at the pin. The next one is minor. It's not a major issue. This is just a byte that contains an error code. So anytime that we're going to transmit or receive from the ADS, we want to make sure that the command was acknowledged. And I'll go into detail with that later. Next, we have the pin connections. Now, we're going to tell the Arduino what the pins are going to do. As you can see here, I substituted ready to equal number 7. Remember, we're going to use pin 7 on the Uno R3 board. So I want the integer labeled ready to be number 7. Now this helps in programming because if you have multiple ones, then this will tell you which pin is which, and it makes things a lot simpler. Now, the second part here, which is the Uno pin 17A4 and 18A5, which shows you which pin on my ADS is connecting to, this is just for reference only. We don't have to tell the Arduino which pins are going to be used for the I2C. That's already part of the library. The only reason it's here is because I wanted to show you as a reference that the Arduino is already set up to use those two pins. All we have to do is connect the ADS to the appropriate pin. Next, we are going to set the register's addresses. And I've got these set up as a label. So if I need a specific register, I don't have to remember the binary number. I could just set a label. I'm going to call it conversion register, and this is going to represent all zeros. This is going to tell the ADS that I want this register. But instead of trying to remember all the binary bits, I just have to use conversion register. The Arduino does the rest. Same thing for the configuration register. I've got the low threshold register and the high threshold register. These are what's called pointers. This instructs the ADS which register we want access to. Now we are ready for configuring the ADS. Now, the first part is the most significant byte. This is going to be bits 8 through 15. Now, because the register is in 16 bits, we have to split it in two. We have what's called the most significant byte, which is bits 8 through 15, and we had the least significant byte, which is bits 0 through 7. Now, as a reference, I put the pin designation or bit designations to show what each bit reflects, what each bit will function as. Then this way, if you ever have to go back into the program and make some changes, you have the reference right there, and all you have to do is do a quick change in a bit, and you're done. It's affected throughout the whole program. Now, so here I labeled this for the MSB config to contain the following bits. Now, you don't have to worry about the 0 and the B. That tells the Arduino that we're going to send this in as a binary format. So, now to read this, you're going to read it from left to right. Um, this being bit 15 and this being bit 8. So when you set these, you want to remember that it's read from left to right. So if you need bit 9, you want to make sure you're using this bit here. So you always want to make sure you're getting the right bit. Now this one is configured to single in continuous conversion. It's going to use one input, which is A0. It's going to be a continuous conversion, meaning that it's going to, once the conversion is done, it's going to start the next conversion, and so forth and so forth. Now we're going to use the 5-volt reading, because as you can see here, bits 11 through 9 is going to show the programmable gain amplifier. And since it's all zeros, it's going to be 6.144 volts. So technically, we're going to use 5-volt reading. And of course, it's going to be a 0. Now, the next part, which is the second half of the byte, is going to be the least significant byte. This is the lower end of the configuration. Again, I've got my reference to show what each bit is and what options I have for those bits. Here I'm going to label it LSB config or CFG, and this is the bits that's going to be set. This is going to be bit 1, or I'm sorry, this is going to be bit 7, and this is going to be bit 0. So you want to make sure that you have the right bit in the right position. This will tell the ADS that we're going to have 8 samples per second, traditional mode, and it's going to have the alert pin pulse high after the 4th conversion. So now we have the initial part set up. And this comes in handy. So if you need to change something, all you have to do is change it right there, and it affects everything in the program. Now we're going to do the initial setup of the Arduino and the ADS. First, we need to tell the Arduino that the ready pin, which is pin 7 on the Uno R3, we're going to set it as an input, meaning that it's going to sit low and wait for data to come in. We're going to read data. Next, we're going to have the serial uh, aspect to it. We're going to set it at 9600 bits per second. This is to communicate from the Arduino to the computer so we can display the results. And we're going to do it at 9600 bits per second. Then we're going to set the wire for the I2C. We're going to set the I2C bus as the master of the I2C bus. The Arduino is going to be the master, means it's going to control the communications on I2C bus. Now, the next part is we need to disable the high threshold and the low threshold. Now, in order to get the program to pulse the alert ready pin, we need to have the high threshold and the low threshold disabled. And that's where this section comes in. So, first, we are going to address the ADS-A, which remember is address 48. We're going to get an acknowledgement from the ADS at this address. Now we're going to send the data telling the ADS we need access to the high threshold. Now we're going to send the most significant byte first, which is going to be bits 15 through 8. And it's going to be the first bit 15 is going to be a 1, and the rest is going to be a 0. Then we're going to send the second part of it, and it's all zeros. Now, the error is the one I was showing you earlier. This is going to let us know if there was any problems with the communication. Now, I'm not going to go into detail as to the different error codes that you can get, but in this problem, I want to know if there was any problem whatsoever. then I can go back and figure out what went wrong. But this is just for demonstrations. So as long as the error equals 0, then it's going to acknowledge that the command was accepted. Now, if it's a 1, 2, 3, 4, or anything other than a 0, then it's going to say the command failed. And this gives me an acknowledgement that, something went wrong. I had to go back and see what went wrong. But I'm not going to go into details of the error codes, not in this video. Um, Now, once I send those commands, I want to wait 10 milliseconds because I want to give the Arduino enough time, or not the Arduino, the ADS enough time to complete the task. Then we can move on to the next one. Next one, we're going to do the exact same thing, except this time it's going to be the low threshold. So this time we're going to send first a 0 and then all ones. And then the second byte is going to be all ones. Now, have you noticed that the bytes for high threshold and low threshold are opposites? And you'll see right here uh, that this is going to 1 and all zeros, but this one is a 0 and all ones. So as you can see, they're opposites of one another. This is going to disable the low thresholds. We're not going to use them in this demonstration. Again, we are going to check to make sure there's no errors and that the ADS did accept the command. Now, we are going to wait 10 milliseconds to make sure that it does complete the command. I had to add that command in there because I just realized, well, I made a boo-boo. I forgot to put that command in there because I wanted to wait 10 milliseconds for it to complete the task before it goes to the next task. So, yeah, I added that in there. Once we're finished, now we can configure the configuration register and instruct the ADS on the task at hand. So this time we are going to do the exact same thing. We're going to address the 48 device on address 48. We're going to point to the configuration register, and then we're going to send the most significant byte configuration, which we looked at earlier, and then we're going to send the least significant byte configuration. This will set the configuration register. Now again, we're going to check, make sure that there's no communication problem. And this is the initial setup. Now anything under the setup loop is just a one-time configuration. It won't run it again unless you either reset the device or you power cycle the device and then it starts over again. But this is the initial instructions to set everything up before we run the task. Now, in this section is the loop. Now, this is a loop where it runs continuously. Once it runs all the commands, it goes back, starts over again. This is the loop. So, before we do any instructions, we're going to wait 10 milliseconds before we do the next task. Now, because that we're having the ready pin pulse at the end of forced conversions, we need to wait because there's no sense in trying to read data from the ADS because it's going to ignore you until the conversion is ready. So what we're going to do, I created this command to sit there and wait until something changes on the ready pin. So as you can see, there's nothing in here. It's just going to loop as long as the ready pin equals 0. Whether it's off, low, this is their representation of off and low. It's a 0. It's a logic 0. As soon as it changes to 1, then it's going to run the following command because this is telling us that the ADS has completed the conversion and it's ready to be read. So let's go ahead and read the data. Next thing we're going to do is we're going to request the data from the ADS. We're going to address the ADS. We're going to point to the conversion register. And we're going to request the data from the ADS. Here we have the ADS address. We're going to request 2 bytes. Now remember, when we receive data from the ADS, it's going to be the most significant byte first. So we do need to make some changes to that. We want to make sure that the bits are in the right location. Otherwise, you'll get completely different results than you intended. So you always want to make sure that you understand you're going to receive the most significant byte first, then the least significant byte. So the first thing we need to do is we sent the request to the ADS. The ADS is going to respond and send us the following code or the following values. Raw value, as I mentioned earlier, is going to handle and store this data that we are receiving. First thing is we're going to read the first 8 bytes and we're going to shift it 8 places to the left. Because as it's coming in, it's going to be the least significant byte. So we have to shift it to the most significant side of the memory or the value. If you don't, you're going to get the wrong values and your program isn't going to work right. So as we're coming in, we need to take the 8 bits, shift it to the 8 places to the left, then we're ready for the least significant byte. Now, once we have the information, we have our 16-bit value. Now we need to convert it. Next, we need to check and see what the value is. Now, according to the documentation to the ADS1115, for the PGA to be set to 6.144 volts, that means that for every unit that is measured, it's going to be representing 187.5 microvolts. Now, it's going to fluctuate somewhat because it depends on the Arduino and the ADS. So you may have to fine tune it, and I'll show you why. As you can see here, our next phase is this one here. We're going to convert it from the raw data to an actual value that I can use. So to do that, we're going to use the float command. Now float allows us to use decimals to do math in decimal places. So as you can see here, our converted value is going to equal the raw value multiplied by 186.5 microvolts. Now that's not a typo. Okay, the documentation says 187.5 microvolts. However, upon my experience with the setup that I have, it turned out to be 186.5 microvolts. So as you can see, there's not a lot of change. Not very uh, di- uh, very different between the two. So you can use your test meter and all that to fine tune it if you have to, but that's just an example. So as we're going to do, I'm going to do 186.5 microvolts, and it's going to store that result. Now we got the result, we're ready to display it. So down here as the last set of commands, I have it printing the information to the screen. We are going to take the raw data. I'm going to show you the raw data that is received from the ADS. It's going to be multiplied by 186.5 microvolts, and this is going to show you what the final voltage is in 3 decimal places. Here I have converted value, and I want to show 3 decimal places. So that's why I have the 3 here. So let's see if it works. We go up here and click upload. You'll see all the information down here at the bottom. Okay, we got a confirmation, no errors. The Arduino is ready to go. So let's see what the results are. Let me open up my serial monitor. Now you can see up here, let me stop this for a moment. You'll see up here where it said command acknowledged. That means that it accepted my commands and instructions. And then as you can see here, it starts to print out the raw data on the left, what it's going to be multiplied by, and then the final result. So as you can see here, it slightly fluctuates. Not much, but slightly. And it's just that last digit that's actually fluctuating. Now, if you look to the right, it's only showing 3 decimal places. Now, as you can see, it changes from time to time. So we're seeing anywhere between 3.264 to 3.265. That's 3 decimal places. Now, if you change it, I can go as high as 6 if I want. And this is why you have to be careful, because even though the raw value, as you can see here, has only got one digit that's changing, you can see on this side here, if I go 6, the last 3 numbers constantly change. Now, I don't have any kind of filtering or anything like that. I'm just doing a demonstration to show how to communicate and use the information it provides. So that's why I just use 3 decimal places, because it's pretty accurate from that point. You don't really need to say anything that small when you're just measuring voltages, or at least in this case. Now you may have to go smaller um, depending on what you're measuring, but this right here is pretty much all I need for this test. So I'll go ahead and switch it back to 3, and then we'll run the command, and this is what's being reported. And as you can see, it's fairly simple. We took this raw data, multiplied by 186.5 microvolts per unit, and got the results of 3.264 volts. Now, for a 3.3 volt line, that's what it's supposed to be. As you can see, it's not far off. I mean, I can just take it, change it to 1 decimal, run it, and see it'll show 3.3 volts, because the Arduino is rounding off to the nearest number. And I believe it's rounding it up to the next number. And as you can see here, that's what it's doing. So the more decimal places you have, the more precise that you can get, but the more sensitivity you're going to get, and possibly more noise. But I always use a standard as 3. No, I don't need 13. Let me put it back to 3. And there we have. Just very simple tasks that you could do. Your raw data, and this is what it is. This is 186.5 microvolts per unit. Comes out to 3.264 volts. Well, I hope this was informational. I hope it helped you understand how you can use the ADS. It's very simple to use, as you can see here in the program. Do stay tuned. I will have other programs to show how to use other features of the ADS1115. So be sure to subscribe and like the video if you like the video. And hopefully I'll see you next time. I'm your host, Mr. Fixit. Thank you for watching.